Hello everyone, my name is Sharbaf, a recent PhD graduate working with Dr. Pore at Penn State University. The work I'll be presenting today will be more about SCM's alkali content, how they affect the pH of pore solution, and I will present a new test method for determining the amount of soluble alkalis in the SCMs. This project was funded by Federal Highway Administration, and it was a joint project between Penn State, Purdue, and Clarkson universities. So ASR is a serious durability issue, and SCMs are commonly used in concrete to mitigate ASR, as this work by Mike Thomas shows. SCMs can significantly reduce the ASR expansion. SCMs mitigate ASR through various mechanisms like Portland consumption, improving permeability, but the main factor causing SCMs to mitigate ASR is reducing the pH of pore solution or hydroxyl ion concentration. As you see, that the more SCMs we have, we're expecting the pH to become lower, and it would help us to mitigate ASR. So how SCMs could reduce the pH, it will be through two main mechanisms. I've tried to show them in this cartoon here. The first one will be called soluble alkalis in my research, and the next one will be alkali binding. So in the first stage, when the SCM is mixed with water, we would expect just part of the alkalis, sodium and potassium particles, to get dissolved. The rest, in fact, will be bound in insoluble phases. As the cement hydration happens and goes further, CSH will form, part of the alkalis will get bound in hydration products, and the rest will become available in the pore solution. So these are the alkalis which their hydroxyl ion later on can attack the unstable, mid-stable structure of silica in reactive aggregates and initiate ASR. In fact, there is a need for determining what portion of the alkalis in SCMs will become soluble and what portion will be bound in insoluble phases. ASTM C311 Available alkalis. So there was some talks before me about the SCM's alkalis and the ASTM C311. ASTM C311 Available alkalis is trying to mix both stages, and I will explain in my next slides, but the available alkalis in the C311 will be somewhat the mix of the two and will give us the available alkalis. A concern with most of the non-traditional SCMs is their high alkali content, specifically with volcanic ashes. Again, the previous talks were kind of touching on it. So I have benchmarked the total alkali content of SCMs. 14 SCMs, in fact, were studied in my research. I've benchmarked this against the Portland cement. As you see, 1.1% of the alkalis for Portland cement, and the majority of the SCMs have alkali content more than that. It will raise a question if they can still mitigate ASR or not. And the ultimate goal of my research, which is still going on, is try to predict the pH of pore solution when an SCM is incorporated into concrete based on various SCM properties. So more details about ASTM C311 Available alkalis. In this test, 5 grams of SCM will be mixed with 2 grams of lime, 10 milliliters of water, sealed in a vial and stored at 38 degrees C for 28 days. After this period, the paste will be crushed, ground, and then it will be filtered, washed with hot water 8 to 10 times, and then the filtrate will be analyzed through ICP method to determine the sodium and potassium in the solution. Shortcomings have been reported for this test. The first one is that in this grinding and washing process, some of the alkalis already bound might get released back. Basically, they would get re-released to the solution. And it will give us an overestimate, or it will give us false higher results. The pH of this solution here is around 12.5, which is considerably lower than the real cement pore solution, which is in the range of like 13.5 to 13.9. The test duration, 28 days, might be inadequate. Some of the alkalis might get released beyond this test period. And this SCM to lime ratio, which is like 2.5, seems to be too high. More lime will be required for very highly reactive SCMs. Again, an example will be volcanic ashes. In light of all these limitations and shortcomings, we developed a new test method at Penn State. It was inspired by Rylam test method for the released alkalis by the aggregates. So in this test method, we have two bottles. One of them has 1 molar sodium hydroxide, the other one 1 molar potassium hydroxide, and 6.7 gram of SCM will be added to either of the bottles. For the bottle on the left, the soluble potassium will be measured, and for the one on the right, the soluble sodium will be measured. The combination of the two will give us the soluble sodium and potassium over time. These bottles will be maintained at 38 degrees C for a period up to 6 months, and the alkali release will be monitored over time. A sample will be extracted from the bottles, filtered, and then they will be sent for ICP analysis to determine soluble sodium and potassium. Separated bottles were dedicated for various ages to avoid carbonation and contamination during opening and closing the cap. In terms of results for the soluble alkalis, the new test method that I just explained, here is the results for volcanic ashes, the 3 VAs I had in the study. So in these graphs, the left one is the soluble sodium, the right one is soluble potassium, x-axis X is of course the time, and y-axis is the concentration of sodium. So this one is the bottle with 1 molar potassium hydroxide host solution. For each of the SCMs, you will see one solid line, trend line, which is showing the soluble alkalis, and then the color-matched dashed line is showing the total sodium in the bottle, or the total sodium from the VA1. For the example, is this light blue color volcanic ash. Majority of the SCMs, the soluble alkalis got plateaued at 56 days. But it wasn't the case for all of them. An example, again, is VA1. The soluble potassium continued to increase up to 6 months. I won't present all the results in this format for all the 14 SCMs, but I will present them in the format of percent weight, in my next slides. Before that, a question I've tried to answer is if this new test method is sensitive to the test conditions. So in a pair of bottles, I reduced the host solution concentration from 1 molar to 0.7 molar. And in another pair of bottles, I reduced the temperature from 38 to 20 degrees C. I wanted to see how these two factors would affect the soluble alkalis. And the results, again, are shown in these two bar charts. So the dark blue ones is showing the original method with 1 molar and 38 degrees C. And the gray ones are reduced molarity to 0.7. And the orange one is showing the reduced temperature to 23 degrees C. So as shown, the effect of reducing temperature was more significant, or for one of the cases equal to reducing the pH of pore solution, the pH of host solution. So getting back to the original test method, the soluble alkali and C311 available alkali results in terms of sodium oxide equivalent for all the 14 SCMs are shown in this figure. Ground glass having a lot of alkalis, a different unit was used for the y-axis. So as you see, for the majority of the SCMs, the soluble alkalis over time surpassed the C311 available alkalis. This is suggesting the 28-day test period for the C311 might be inadequate, and more time will be required for the alkalis to get dissolved. Another observation is, again, benchmarking against the OPC, you see the majority of the SCMs are in fact adding more alkalis to the pore solution compared to the cement itself. So general belief that the alkalis in the concrete is coming from the cement only when we have SCMs. My results is showing that is not true for all the SCMs. Examples here, again, Class F fly ash, Class C fly ash, you see both of them, the soluble alkalis are even more than the cement. So here the question would be, when we replace a portion of cement with these SCMs, should we still expect the pH of the pore solution to reduce? So to answer this question, I made the real cement paste, incorporating all of the 14 SCMs at 20% replacement level, and I went through the pore solution extraction to see if how in fact these SCMs would affect the pH of pore solution. On top of the 14 SCMs I had one mix with cement only and one mix with an inert material, quartz flour, to kind of compare this quartz flour results or inert material with the 14 SCMs I had. And the pore solution was extracted as these time intervals shown up to 1 year. So in this slide, I will present the pore solution results for the natural pozzolans and ground glass. Next slide will be coal ash products. So OH minus concentration in the pore solution on y-axis, the time on x-axis. So the three black color lines, the very top one is Portland cement only. This line here is theoretical dilution. It's basically 0.8 times the cement only mix. And the solid black line is showing the real dilution through quartz flour. When an SCM reduces the pH below the inert mix, it will be called as a net alkali sink. It means it's doing better than the cement dilution only. As shown for all the calcined clays, that was the case. The pH was reduced below the inert material. For volcanic ashes, in spite of all the alkalis dissolvable into the pore solution, they still reduced the pH below of the inert material. For the ground glass, considering like the high amount of total and soluble alkalis, it could not do the same, but it was lower than the cement-only mix. For the coal ash products, the three ground bottom ashes, except for one of them, the other two did a good job reducing the pH. And for the case of FPCs, this was not the case. For the two fly ashes, class F fly ash lowered the pH below the inert, but class C, as we expect, and I will explain more about it, class C could not do the job and reduce the pH below the inert material. So again, my ultimate goal was try to predict what will be the change in the pH of pore solution when an SCM is being incorporated. So if this change from the inert material to any of the SCMs be called bound alkalis, I'll try to suggest a model for predicting this value, like the bound alkalis at 6 months, like 180 days. Multiple linear regression analysis was used, various SCM properties, including available alkalis, soluble alkalis, reactivity was evaluated to basically suggest the best possible model. So if we just fix water to cement ratio and replacement level, as these are the two parameters was fixed in my research, 0.48 for water cement ratio and 20% replacement level, but the others will be different for various SCMs, like the soluble alkalis through the new test method I just explained, reactivity, ASTM C311 if I don't mistake, R3 paste reactivity now, and bulk chemistry, calcium over silica plus alumina ratio. So Hung and Glasser work is showing like this is the one of the main factors showing how much of the alkalis could be bound by CSH. Two models are developed, one for predicting the amount of bound sodium and amount of bound potassium, and predictors are listed here. Again, reactivity, soluble alkalis, and calcium over silica plus alumina ratio. R-square value of 91 and 81% are showing the model is doing a pretty good job. But if we want to just have the pH, the OH minus concentration, we know at later ages we like have only these two ions, the other ions will be kind of negligible. So the sum of the two equations I had on the previous slide will tell us how much changes in the hydroxyl ion concentration we would have in the pore solution when an SCM is incorporated. Just to conclude, a new test method was suggested for determining the amount of soluble alkalis. Up to 87% of sodium and 98% of potassium might be soluble. Comparing the soluble and available alkalis, the 28-day test period for ASTM C311 available alkalis might be inadequate. Pore solution data shows, despite of high soluble and total alkalis, specifically for volcanic ashes, they still serve as a net alkali sink, and they reduce the pH. And hydroxyl ion concentration reduction by SCMs can be predicted using three predictors: soluble alkali content, reactivity, and calcium over silica plus alumina ratio. This research is still going on. We're trying to use thermodynamic modeling to also consider the effect of water to cement ratio and replacement level, and kind of make the model more global and generalized for all the concrete mixes. With that, thank you very much, and I'll be happy to answer any question and discuss any comments.